The definite integral f to b of f of x dx is called an improper integral if any of the following is true. If at least one of the following is true. If a is infinite, so that means a is infinity. So if a is infinite, if a is infinite, if b is infinite, if f is discontinuous at a, if f is discontinuous at b, let me. At b, how about if f is discontinuous at a c, and that c is between a and b. So if you notice, I just made up an abbreviation for discontinuous, so forgive me about that. All right. One thing I want to point out is that only one of these conditions have to hold for the integral to be improper. So an improper integral can be expressed using limits. We use limits to express improper integrals. So the goal is, if you have an improper integral, you want to convert it to a limit problem. Right? Now, if the limit exists, if this limit problem you have, if the limit exists, which says the integral, the improper integral is convergent. Otherwise, the integral is divergent. All right, let's do some problems. Assuming we have the integral from 1 to infinity of 1 over x squared dx. Okay. This is an integral that we know about, but if it were an indefinite integral, then this would be an easy integral. But this is now a definite integral. So let's convert it to a limit problem. Instead of having the infinity there, we rewrite it as limit as maybe b, limit as b goes to infinity, 1 to b, 1 over x squared dx. Now we can now solve the integral and then let the limit of b go to infinity. So this gives us limit as b goes to infinity of, if you find the antiderivative of 1 over x squared, it's negative 1 over x, and then you're going from 1 to b. So this becomes the limit as b goes to infinity of, let's bring out the negative sign, and then we have 1 over b minus 1 over 1. Okay, so this is like limit as b goes to infinity of 1 minus 1 over b. And if we let b go to infinity, this part of the integral, this just goes to 0 if b goes to infinity. So for that reason, this limit, this integral is 1. Okay? And we say it's convergent. Okay. Now, graphically, what does this look like? So we have this is the graph of 1 over x squared, and maybe this is 1, and this is b. So what we're trying to show with this integral is that if we let b go to infinity, the area is a finite area. You would assume, you'll be thinking that if we let b go to infinity, which means that if we just keep summing up everything till infinity, like including here till infinity, that the area under the curve is going to be an infinite area. But it turns out that the area is just 1, right? Area is 1. So this area, the whole area as b goes to infinity actually is equal to 1. So let's assume b goes to infinity, so that means we get rid of this b here. Okay. Let's look at another integral. So how about 1 to infinity of 1 over x dx? Again, we start by expressing it as a limit problem. Limit as b goes to infinity of 1 to b of 1 over x dx. In this case, this becomes limit as b goes to infinity of natural log of the absolute value of x, and then we're going from 1 to b. Okay, so this is limit as b goes to infinity of natural log of b minus natural log of 1. Natural log of 1 is 0. So this is 0. And we know that as b goes to infinity, natural log of b goes to infinity. So this is divergent. Okay? And if you look at this, if you look at the graph of 1 over x, it sort of looks like the graph of 1 over x squared. But magically, 1 over x squared converges, 1 over x doesn't. I mean, it's just the tail is fatter. Let's put it that way, like this. It's a little fatter than this. But still, it's I think it's amazing that when you add up the area from 1 to infinity, that this goes to infinity. Meanwhile, that of 1 over x squared goes to 1. All right, so we've seen a convergent integral, convergent improper integral, and a divergent improper integral. And again, what makes these two integrals improper? Because one of the limits is infinity. Okay, so let's try another one. So okay, number 3, the integral from negative infinity to 0 of x e to the x dx. All right, so we have to rewrite this as the limit as b goes to maybe a this time. Let's use an a this time. So a goes to negative infinity. It doesn't matter what you use, but I just want to use a because it's a lower limit. A to 0, x e to the x dx. All right, so if you do this integral if you perform the integration using integration by parts, we've done this before, but I think you should try it. Make u x and v e to the x dx, integration by part, integration by parts. That's all I'm going to say. If you do that, you end up with limit as a goes to negative infinity, and what we have is x e to the x minus e to the x, and then you're going from a to 0. Okay, so if you do that, so after integrating x e to the x, we get x e to the x minus x, I believe. Okay, so if you do that, you end up with limit as a goes to negative infinity of, you plug in a, that becomes a e to the a, I think, minus e to the a, right? Then when you plug in 0, no, you gotta plug in 0 first. Plug in 0, you get negative e to the 0, which is 1. Okay, let me be clearer. You plug in 0 into this whole thing, right? If you plug in 0 into the whole thing, you're going to end up with negative 1. All right? And then you plug in a and you subtract. When you plug in a, you're going to get a e to the a minus e to the a, right? And if you subtract, this becomes positive. Just do it, try it yourself. Okay. So you plug in 0 and plug in a and subtract, this is what you get. Now we have the limit. Let's take the limit one at a time. So this is limit as a goes to infinity of negative 1. That's quite easy. And then we have minus the limit of a e to the a as a goes to negative infinity, and then plus the limit as a goes to negative infinity of e to the a. Okay, so now look at this. The first one is just negative 1. So let's take them one at a time. Only one of them is going to give us a hard time. But let's see how we can rewrite things to make it easy. So we can say this is limit as a goes to negative infinity of negative 1 minus limit as a goes to negative infinity of, I'm going to write it as a over e to the negative a. And I'll tell you why in a minute. Plus limit as a goes to negative infinity of e to the a. This remains this is a constant, so this is just negative 1. Let's go to the third one. This, we're looking at negative infinity. As a goes to negative infinity, this becomes e to the negative infinity, so this goes to 0. Okay, so we are left with this. This one, we're going to apply L'Hopital's rule. Okay, so let's apply L'Hopital's rule. So this is limit as a goes to negative infinity of a over e to the negative a, you take the derivative. L'Hopital means you take the derivative of the top and you take the derivative of the bottom. So again, I'm gonna say that. So you take limit as a goes to negative infinity. Derivative of the top is 0 with respect to a. So, oh no, not 0. What is wrong with me? It's 1. 1. Derivative of the bottom is negative e to the negative a. Okay. So now, plug in infinity. If you plug in infinity to negative e to the negative a, or if you plug in negative infinity, think about that. This is not the best way to do it, but I'm going to do it that way to just demonstrate to you. This is e to the negative infinity. So this becomes e to the negative infinity. This. So the denominator now is kind of negative infinity, which is huge. So you're dividing something small, a small number like 1, you're dividing it by something very huge. So this goes to 0. This is 0. Okay? So that means our definite integral becomes definite improper integral becomes negative 1 minus 0 plus 0, which is just 1. Okay? All right. Which is negative 1. I said 1. What is wrong with me? Now let's try another problem. Let's try okay. Number 4. Let's do the integral from negative infinity to infinity of 1 over 1 plus x squared dx. All right, 1 over 1 plus x squared rings a bell. It's the derivative of inverse tangent or arctangent, right? But if you look at this, you will see that we have negative infinity to infinity. Whenever you have negative infinity to infinity, you want to break it up into 2 improper integrals involving at least one of the limits being a finite number. So we go from negative infinity maybe to 0, yeah? Of 1 over 1 plus x squared dx plus 0 to infinity of 1 over 1 plus x squared dx. So this changes our problem to 2 integrals. So we can do limit as a goes to negative infinity of a to 0, 1 over 1 plus x squared dx, plus the limit as b goes to infinity of 0 to b, 1 over 1 plus x squared dx. Okay? So this becomes the limit as a goes to negative infinity of the arctangent, inverse tangent of ax going from a to 0 plus limit as b goes to infinity of the inverse tangent of x going from 0 to b. All right, so we're gonna do limit as a goes to negative infinity. If you plug in 0 and you plug in a, so the inverse tangent of 0 is 0, and then you have minus inverse tangent of a plus limit as b goes to infinity of the inverse tangent of b minus inverse tangent of 0, which is 0. All right, so here we're just dealing with the limit as a goes to negative infinity, because this is happily 0, this is 0, and this is 0. So the inverse tangent of a as a goes to negative infinity, right, is actually pi over 2, negative pi over 2, and then you multiply it by negative, you multiply by a negative in front of it, you get pi over 2. And the function we're dealing with right now is the inverse tangent. Maybe we should draw it to see. So the inverse tangent is this function. It goes like this. This is pi over 2. This is negative pi over 2. All right? So as you go to negative infinity, the value is negative pi over 2. As you go to infinity, the asymptote, horizontal asymptote, is pi over 2. All right? So we have negative, as we go to negative infinity, this is actually negative pi over 2, and then you multiply by a negative, you get pi over 2. Now, as you go to infinity, this is just pi over 2. So you have plus pi over 2. So your answer is pi. Okay? So this was the original, this was the antiderivative. But now let's go back to the original function. This is the original function. If you sketch this function, this is what you're going to get. I'm going to sketch it in green. You're going to get something like this. All right? So x-axis. So this is telling us what we just found out is that the area from negative infinity to infinity of this function, the area is actually pi, the area under the curve. Okay. All right, let's try another problem. What number is this? I think we just did number 4. Let me check. Okay, number 4. Call this number 5. For what values of p is the integral 1 to infinity over 1 over x to p dx? For what values of p is this integral convergent? All right. So, since we're now students of integrals, one value of p pops out when p is 1. The integral becomes integral 1 to infinity of 1 over x dx. And if you think back, go back to our second example, this integral is divergent. So we're gradually finding the answer to our problem, the question. So when p is equal to 1, the integral is divergent. Okay, now let's look at how about when p, case 2, when p is greater than 1, what happens then? So this would be 1 to infinity of 1 over x to the power of p, right? Which would be limit as b goes to infinity of 1 to b 1 over x to the power of p dx. All right, so this is limit as b goes to infinity of integral 1 to b x to the power of negative p dx. So this is limit as b goes to infinity of this is x to the power of negative p plus 1 over negative p plus 1, right? And then we put 1 here, we put b there. Okay, now we're going to substitute b. We're going to substitute b for x. So if you plug in b for x, you get b to the power of negative p plus 1. You got to keep track of what we're doing because it becomes a little shaky here. Minus p plus 1. So that's when you plug in b. So let's not forget our limit. And then you plug in 1. When you plug in 1, you get 1 over negative p plus 1. You see that? Now think of b. Think of b. Let's let b go to infinity. Or before we even do that, there's something we can factor out. We can factor out negative 1 over p. Sorry, negative p plus 1. We can factor that out. So let's factor it out and let's write it as 1 minus p. So we're left with b to the power of negative p plus 1 minus 1. Okay? Okay? So how about this? I'm going to write this as case p is not equal to 1 because this applies to every case when p is not equal to 1. So this is the limit. This is the value of our integral when when p is not equal to 1. Now, how does this change depending on the value of p? If you look at this exponent, if p is 1, then the exponent of b is 0. Okay? But then if p is 1, then the denominator here is 0 also. So this integral, this value of the integral is not valid when p is equal to 1. That's why when p is equal to 1, we resort to natural logarithm. All right, so we have to focus on when p is not equal to 1, which is the case here. So when p is not equal to 1, p is either greater than 1 or less than 1. So let's look at the first case when p is greater than 1. So let's call it case 2a. P is greater than 1. If p is greater than 1, look at our limit. Right? If p is greater than 1, b is still gonna be well, if p is greater than 1, the exponent of b is going to be negative. It's still going to be negative. So, and if it's negative, it doesn't matter how large b becomes. In fact, if it's negative and b becomes really large, if you're raising something really large to a negative power, the value goes to 0, right? So let's focus on this. If this value is negative, p is greater than 1, then this means that then negative p plus 1 is negative. It's a negative number. And if it's negative, this value goes to 0. So b minus p plus 1 goes to 0, right? As b goes to infinity. All right. So for that reason, our integral 1 over x to the p dx, since this is going to go to 0, this is going to go to 0. Since it's going to go to 0, then that means that we're just left with negative 1 over 1 minus p, right? Okay. Okay. So, I'm gonna, okay. That's if p is, okay, good. All right, now case 2b, I want you to check for yourself, confirm that the integral 1 to infinity of 1 over x to p dx diverges. Just the same argument. Use the same argument I used over here. So we can develop a result. And I want you to remember this because this is going to be so useful in the next chapter. The integral from 1 to infinity of 1 over x to the p dx is convergent if p is greater than 1 and divergent if p is less than or equal to 1. So that's the result we're going to take away. Okay? All right. There's a problem I want you to try. It's an improper integral, but it doesn't involve infinity. So this is integral from 0 to 3 of 1 over x minus 1. Okay? The graph of 1 over x minus 1 is that. So you have that. All right? So there is a discontinuity at 1. So you're going from 0. Let me draw this to scale. Let me draw it to scale. So okay. Okay, so this is 1, 2, 3. And we're going from 0 to 3. However, the graph of 1 over 1 minus x is, let me go with light blue here. Is that, and then this. So what we are looking for is the area from 0 to 3. So we want this area. But then, mind you that it continues and keeps going. And it keeps going here. So the question is, does this integral converge or diverge? So that means, is the area a finite area or is it an infinite area? All right. So since this function is discontinuous at 1, my hint is for you to break it up, go from 0 to 1, 1 over x minus 1 dx, plus 1 to 3, 1 over 1x minus 1 dx. Okay, so you're going to be doing limit as b goes to 1. You're approaching 1 from the left, of 0 to b, 1 over x minus 1 dx. And then you're doing the limit as b goes to 1 from the left now, or from the right, or maybe a, call it a. The integral from a to 3, 1 over x minus 1 dx. Okay. So I want you to verify this. My answer that I got is that it diverges. Why? Why does it diverge? Okay. And I also want you to try another one. Try the integral from 0 to 1, natural log of x dx. I want you to set it up and do everything. And tell me what's your answer. I'll ask you in class. Okay? It converges, but what does it converge to? All right. We're going to stop here, and I'll see you in class.